Suppose that P is the set of all people, and we define H to be the set of all Pn in P cross N, where N is the set of all naturals, such that P has N children. H has a very important property where for any element in the set of all people, there exists exactly one element of the natural numbers in which it is H related to. We express and describe this property in relations by saying that a relation is a function. But what exactly is a function? Well, if we suppose that f is a relation from a to b, then f is called a function if and only if, for all a and a, there exists exactly one b in b that a is f related to. And to indicate that a relation f is a function, we write this notation here with the colon or semicolon. I forgot what this was called. And then this arrow from A to B. So for example, if we let A be the set of 1, 2, and 3, and B be the set of 4, 5, and 6, and let f1 and f2 be defined as this, then we can see that f1 is a function because each element of A is the first coordinate of exactly one ordered pair in f1. But we can see here that f2 is not a function because 1 is the first coordinate of two ordered pairs in F2. Or in other words, 1 is F2 related to not exactly one element of B. So this makes F2 not a relation. I mean, it is a relation, but it's not a function. Suppose that f is a function from a to b, and this a is an a. Then, by definition of function, then we know that there exists exactly one b in b that a is f related to. This specific b that a is f related to can be called the value of f at a, or the image of a under f, or simply just f of a. We actually denote this specific b for any a in a by this notation. And when we write this notation, we call it f of a. And this notation should be pretty familiar to you if you've lived before. So for example, if we let a be the set of all a, b, and R2 such that b is equal to a squared, if we let x be an arbitrary real number, then we could say that f of x is equal to x squared. A function f from a set A to another set B is often specified by giving you a rule for how to find f of a for any a in a. And in the last example, the function f did the exact same thing, and you can actually define f using that rule. And in this case, the function f tells you how to evaluate any real number x and get f of x, which is just square x. And it's often very useful to think of any functions that you come across like this, where it gives you a rule, a specific rule, on how to find f of something in a set. But just keep in mind that not all functions need to be like this. Just by definition, a function is just a relation from a to b that has this property. It doesn't have to have a specified rule or one that's noticeable, or yeah, it doesn't have to have a rule. It just has to have this property. Many, actually likely all, real valued functions that you will come across will be ones that are defined through rules like this. But again, that's not exactly what it takes to be a function. It's more broader than that. And with that, this theorem says that if we let f and g both be functions from a to b, then if for all a and a, f of a is equal to g of a, then both functions are equal to each other. Or in other words, a function is completely determined by its rule that it gives to evaluate f of whatever is in A. To prove this theorem, of course, it's an if-then statement. We have to assume the if, then prove the then. The next step is to let x be arbitrary and let it be an arbitrary element of the function f, or g. You can do whichever since it's an if and only if. But since it's an equivalence of sets, we will let x be arbitrary and prove that x is in f if and only if it is also in g. First, we observe that x is in f if and only if f of x1. Also, I have to specify. Whenever you see x1 or x2, just note that x is an ordered pair that is equal to x1 comma x2. So, I was about to say that we observe that x is in f if and only if f of x1 is equal to x2. We then notice that this is true if and only if g of x1 is equal to x2, since we know that f of a is equal to g of a for all a and a, since x1 and x2, or not x2, since x1 is in a. So now we can say that f of x1 is equal to g of x1 is equal to x2. And by definition of g of x1 equals x2, this is true if and only if x is in G2. From this, we've shown that x is in F if and only if it is also in G. And since x is arbitrary, we can say this for all elements of F and G. So now we can say that F is equal to G, since that's an if and only if. Since a function is just a special kind of relation, we can use the properties of relations that I've gone over in previous videos to use that in relation to functions too. So for example, if we suppose that f is a function from a to b, then it makes sense to talk about its domain, which is a subset of A, and its range, which is a subset of B. From the definition of a function, every element of A must be the first coordinate of some, or actually exactly one pair in F. So since the domain of F is just the set of all first coordinates in all of its pairs, then it immediately follows that the domain of F is actually just equal to A. But we cannot do the same with the range of F being equal to B, since it is only guaranteed that there is exactly one element of B for any element of A. So the cardinality of B could be greater than that of A if they're finite sets. Yeah, it's just not guaranteed. So from this, we can actually define domains and ranges for functions alone, where obviously the domain of f for any function f is equal to just a, and the range of f can be defined as the set of all f of a such that a is in a. And again, this need not be all of b. This just needs to be a subset of b. So if we define a real valued function f with the rule x squared for any x, first of all, the domain is just the real numbers, since it's a function from the real numbers to the real numbers. Or I guess you could say it's a function on R. The range of f is just the set of all positive real numbers, union the set of 0, since 0 isn't positive or negative. And again, since all functions are just special kinds of relations, we can draw diagrams that represent functions just like how we did in previous videos with relations. And this is an example of that. As we can see here, the diagram that represents a function must have exactly one edge pointing away or starting at each element in its domain set. And that's by the definition of a function and the fact that these edges represent ordered pairs. So if this was A and this is B, then AB is an element of the function. And since functions are kinds of relations, we can also use the definition of composition of relations to define a composition of functions. If we let f be a function from a to b and g be a function from b to c, then by definition of composition of relations, g after f, the composition of g and f, is the set of all AC and A cross C, such that there exists a B in B, where f of A is equal to B and g of b is equal to c. And in fact, if f and g are functions, then g after f, the composition, is also a function. Specifically, this theorem states that if we let f be a function from a to b and g be a function from b to c, then g after f, their composition, is a function from a to c. And also, for all a and a, g after f of a is equal to g of f of a. To prove this, we first suppose that a is an arbitrary element of a. Then we observe that this is true if and only if, by definition of a function, there exists exactly one b and b, where f of a is equal to b. Then we notice that since b is in b and g is a function from b to b, then there must exist exactly one c and c, where g of b is equal to c. And from this, we get that c is g after f of a, by definition of composition. And after using existential instantiation, since b is unique and g is a function, c as being equal to g of b must also be unique. This means, since c is g after f of a, that there exists exactly one c in c, such that c is equal to g after f of a. And by definition of g after f of a, this is true if and only if there is one c in c, such that a is g after f related to c. And since a was an arbitrary element of a, this means that this is true for all elements of a. And that is just the definition of a function, so we have shown that g after f, their composition, is a function from a to c. And to prove this second part, we notice that here, of course, after existential instantiation, that b was f of a and c was g of b, and since c was also g after f of a, then plugging in b equals f of a for g of b gets g of f of a is equal to g after f of a. In the video where I first introduced the concept of composition of relations, I think I pointed out the fact that this arrangement of relations in the composition is kind of like y, like, I don't want to say outlandish, but like peculiar. Like, why isn't it r and then s? Since that's basically what you do for compositions anyway. You do r and then s. Why is it s and then r? And now, since we've gone over all this, I can finally provide the reason for that, in which the reason is just for convenience and ease on the eyes. The composition is s and then r, because if s and r are functions, then we can rewrite the composition as s of r of a, in which s comes before, or not before, like literally, but is written before the r, and then the a, s r a, so we do that. And it's also why I say s after r, since you do r and then s. R before s, s after r. And since, again, functions are just a special kind of relation, we can apply the property of associative composition, for example, with functions too, which just means that when you're doing composition with functions, three or more functions, you don't have to worry about which composition you do first, because it doesn't matter since, it's associative. Anyway, this video's purpose was more for a set-theoretic introduction to functions, instead of the very specific functions that were introduced to in like school and stuff. In which case, functions are introduced mainly as real valued functions, where for example they'll say like, yo guys, a function takes in a number input and spits out another number output, a number x, like x squared or x cubed plus x squared plus e to the x plus 1 on x plus x on 1 plus x on e, blah blah blah. So this video served more of a more general set theoretic approach to functions. Anyway, bye!